In this section, we're going to learn about something called the Epsilon-Delta definition of a limit. The book describes this as the precise definition of a limit. And this goes away from looking at tables or doing removable discontinuities or doing some direct substitution. And this goes into what we call Epsilon-Delta proofs. So I want to give you the little warning and caution. This is not what the basis of the rest of the class is about. This is giving you a very theoretical viewpoint of what a limit is. And I just want to expose you to this, but I don't want anyone to feel like if you don't get it, then you are doomed in calculus. Definitely not the case. So here we go. One of the big things about this is it's going to measure closeness, how close two things might be. So the idea behind this is we're trying to relate how close a value is to the limit, the f of x is to the limit, and compare it to x being close to the value that x is approaching. So we're relating this epsilon and this delta. We use these Greek symbols to signify that. So what we're saying is there's got to be a way to connect these two. And we can use some algebra skills that we have to come up with a way to relate them. And there's a certain format that this is expressed and trying to do the quote-unquote proof for these. One thing I want to point out, if you see something like this, f of x minus L is less than epsilon, that's like saying, that means that negative epsilon is less than f of x minus L, less than epsilon. And if you add L to all the parts, you have L minus epsilon is less than f of x, less than L plus epsilon. And this has some meaning to it as we go along. So I just want to remind people of that relationship for the absolute value of an inequality. Likewise, if we have the absolute value of x minus a is less than delta, that's a lowercase delta, then we can write that as negative delta is less than x minus a, less than delta. And then we can add the a to all three parts, and we end up with a plus delta, a minus delta, excuse me, is less than x less than a plus delta. So that actually comes into play as we go into this a little bit further. And I'm going to show you some other, I want to call them tricks, but approaches to the technique that deal with these lower and upper limits. Okay, here's our definition. Let f of x be defined for all x not equal to a over an open interval containing a. Let L be a real number. Then the limit of f of x as x approaches a equals L. If, and this is the part that becomes our quote-unquote proof, if for every epsilon greater than 0 there exists a delta greater than 0 such that 0 is less than absolute value of x minus a less than delta, then f of x minus L is less than epsilon. And what we end up doing is we define a delta to be a certain value that's related to epsilon with, it could be something added or something multiplied. And then we're able to manipulate it, do things to it, to where we end up with this expression here and the epsilon there. That's the overall goal. I've given you kind of the secret behind what's going to happen. So let's go ahead and take a look at some of these. Okay, this is just a question one. If the limit as x approaches a of f of x is not equal to L, then we can find an epsilon greater than 0 so that no matter how close x is to a, f of x will never equal L, f of x will be getting farther from L, f of x will be at least epsilon units away, f of x will be within epsilon units away. And that's what we're looking for there. Or that one too is kind of close. It is possible for f of x to be, I wouldn't say that last one. Okay. And this is a good graphic of what's going on here. So we have this A here, and it could be delta on one side, delta on the other, so that's where we get our A plus delta, A minus delta. That's the range of values that would satisfy this corresponding range of values over here for the limit. So this range of x values gives this range of y values, and that's what an epsilon delta is about. So over here it's a very narrow range, and it's a narrower range up there. But we're going to find ways to relate the two. There's an interactive applet you can click on in the textbook, so I encourage you to take a look at that. It's kind of fun. So we're going to prove that the limit as x approaches 1 of 2x plus 1 equals 3. So we start off with this. Now I'm going to start writing something, and then we're going to step aside and do some scratch work, what I literally call scratch work, where we can come up with the work behind the scenes to get us to finish off our definition. So we have let epsilon be greater than 0. That's a standard start to this. We're going to choose delta equal to something so that 0 is less than the absolute value of x minus a. A in this case is 1. That's our a. X minus 1 less than delta. And we're going to come back and finish filling in that blank and do some more work here. But I need to do some scratch work here on the side. Okay, let's see. How can we relate these two is a real big question. Well, think about our absolute value of f of x minus L being less than epsilon. This f of x would be our 2x plus 1 minus, and our L is 3, less than epsilon. So that's the absolute value of 2x minus 2 is less than epsilon. And I can factor out a 2, so it'll be 2 times the absolute value of x minus 1 is less than epsilon. And I want to point something out, is that this x minus 1 looks very similar to this x minus 1. In fact, those are the same thing. So if I were to take this 2 and divide it out of both terms, I would have the absolute value of x minus 1 is less than epsilon over 2. And that's what we can identify our delta to be. Oh, I just saw my my boundaries. I wrote outside the boundaries. So let me rewrite this part up here. So that should be, we're going to choose delta equal to, and I leave a blank there, but now I can fill that blank in. We're going to call it epsilon over 2, so that 0 is less than the absolute value of x minus 1, less than delta. Let me make this a little bit smaller. Yeah, there we go. That fits a little better. Okay. And now we can do the following kind of formality. Consider filling in what we just did. Absolute value of f of x minus L is equal to, this scratch work doesn't exist technically for this, is going to be equal to our absolute value of 2x plus 1 minus 3, which will be our absolute value of 2x minus 2, as we just calculated, which will become 2 times the absolute value of x minus 1. And we already said that this x minus 1 is less than delta, where delta is epsilon over 2. So this part can be then replaced with an epsilon over 2 if I do a less than 2 times epsilon over 2. And then what happens? The 2's divide out, and we have our epsilon, which was our goal. And so we can then do this conclusion, these 3 dots. Therefore, limit, let me just state the limit now. Limit as x approaches 1 of 2x plus 1 equals 3. And I may have fallen outside those boundaries again. I think that's better there. Okay. Hopefully you can see it all. And that's it for a problem like this. So we have several more I'm going to do, and hopefully this pattern will make sense to you. Videos to watch. There are steps for going through this. It just summarizes what I've been doing here. Let's try the next one. We're going to prove that the limit as x approaches -1 of 4x plus 1 equals -3. So again, we start with our let epsilon. I got a dead spot on my screen, so I got to write this in the non-dead spot. Epsilon greater than 0. And we're going to choose our delta equal to something. We haven't figured that out yet. And assume that 0 is less than x minus the -1 less than delta. And so, by the way, the absolute value of x minus -1 is x plus 1 is less than delta. And so we're going to work algebraically with this 4x plus 1 minus a -3 to get to something that looks like this x plus 1. So I'll do my scratch work then. And we'd have, we're looking for the absolute value of f of x minus L, and that's going to be 4x plus 1 minus -3. That becomes the absolute value of 4x plus 4, which is 4 times the absolute value of x plus 1. Hey, look at that connection we made, x plus 1 back over here. And so that, if we want that to be less than epsilon, as is the definition, because that was an f of x minus L, we can then divide by 4, and the absolute value of x plus 1 is less than epsilon over 4. So that x plus 1 is the part that's related to delta, so we set delta equal to epsilon over 4. So that goes over here. So thus we have 4x plus 1 minus -3 is 4x plus 4, which is 4 times the absolute value of x minus, or x plus 1, which would end up being 4 times epsilon over 4, which is epsilon. Therefore, the limit exists in that way. Okay? Lots of fun, right? Okay, let's go on to the next one. Okay, another one that's like this. So again, we start with this epsilon greater than 0, and we've got to determine what this delta is going to be, but we know it's going to be the absolute value of x minus 2 is the a there that the limit's approaching. So we do our scratch work. And we have the absolute value of f of x minus L is going to be the absolute value of 3x minus 2 plus, or sorry, minus 4. So that's going to be the absolute value of 3x minus 6, which is 3 times the absolute value of x minus 2. And recall that this is going to be less than epsilon. So that means if we divide by 3, then we would have the absolute value of x minus 2 is less than epsilon over 3. And again, I'm making the connection here between this x minus 2, this x minus 2. So this becomes our delta. So that's going to be epsilon over 3. And now we can put it all together. So thus, 3x minus 2 minus 4 is 3x minus 6, which is 3 times absolute value of x minus 2, which becomes 3 times epsilon over 3, which is epsilon. Therefore, that limit as x approaches 2 of 3x minus 2 equals 4. Okay. Hope you're starting to see a pattern now. This will get more complicated, and we're going to deal with that. Our next one, let's see what our next one is. I think I have another one before we get to, okay, we're going to do the limit as x approaches 2 of x squared equals 4. I thought I had another one in here to do first. Oh, okay. Okay, so we have, again, it's going to be something of the nature, let epsilon be greater than 0, and then delta equals something. We're going to come up with that. And then we'll have so that absolute value of x minus 2, you could say 0 is less than, x minus 2 is less than delta. And we will then finish the rest of this off in just a minute after we can do some scratch work. So I'm going to do my scratch work now. Okay, so what do we have? We have, this one's a little bit different approach. Think of this as, we have the x minus 2, so it's the absolute value of x minus 2 is less than delta, which means that negative delta is less than x minus 2 less than delta. So just bear with me on this process, please. Now, my goal is to, let's think about this x squared minus 4. That's my f of x minus L. That could be factored as x plus 2 times x minus 2. Now, when you have something like this, I want to point out that we start off with this factor, and the goal is then to come up with the other factor and see how we progress to get there. And this will allow us to come up with values, some other ideas. We have to be a little bit creative, more creative now than we were before when it comes to what our delta is going to be. Okay, so in getting to this process, if I want this to be x plus 2, I'm going to have to add 4 to all the parts. So negative delta plus 4 is less than x plus 2 less than delta plus 4. Okay, now one thing I want to point out is if I want to go back to an absolute value, what I can't do right now is I don't have symmetry on this. Because to have symmetry, I need to factor out this negative on the lower end, and then it needs to be identical to what the upper end is, the part inside the factoring. If I factor out now, it would be the negative of delta minus 4. So we can make the upper limit higher, bigger. We can make the lower limit lower. We can't make the upper limit smaller because we don't know if it can go any smaller. And we can't make the lower limit any bigger because we don't know if it can go any bigger. But I can make this lower limit smaller to do the following. If I said that was negative delta minus 4, it's still going to hold true because it's down by now 8 units further, which is smaller than what we had before. And the strategy there is the following. I can factor out the negative, and I have delta plus 4 is less than x plus 2 now, less than delta plus 4. So we end up with the absolute value of x plus 2 is less than delta plus 4. Now we're going to want to, I can't choose a delta that's going to be based on delta itself. It can't be in the definition. So I'm going to have to pick another value. And this is where we have a lot of creativity. Now, we can arbitrarily set delta to whatever we want. So if we set delta, for example, was 1, then we could conclude that the absolute value of x plus 2 is less than 1 plus 4, which is 5. And so that's a factor we can use in terms of our epsilon. Now, what I want to say, so we can say epsilon would be less than 5. And in that case, if our delta is the 1, then our delta would be epsilon over 5 because of this 1 here. So trying to relate this all together. And how do we tie this in? We use this little trick. I won't call it a trick, but technique. We call this the minimum of 1 and epsilon over 5. So now we go forward and we build this up to make it what we had. So we have this f of x minus L, the absolute value of f of x minus L is the absolute value of x squared minus 4, which could be expressed as x minus 2 times x plus 2, the absolute values. Now our x minus 2 is seen as delta, and for that I'm going to call it the epsilon over 5, and for the x plus 2 I'm going to call it the epsilon, as we had earlier, the epsilon, just the 5 that we had earlier. So we end up with an epsilon. And then we could draw our conclusion, therefore, limit as x approaches 2 of x squared equals 4. And that's it. It's kind of weird and crazy, but we draw on the fact that we can take the minimum of the two and we assign these two values, and then we do some kind of algebra in the process. So now we're going to go on to this next one for the square root of 3. It says find a delta corresponding to epsilon greater than 0 for a proof that the limit as x approaches 9 of square root of x equals 3. So recall the way we set this up. We have the absolute value of f of x minus L, and that's going to be the square root of 3, square root of x minus 3, and that's going to be less than epsilon. So what we're after, if we break that out, that's going to be negative epsilon is less than the square root of x minus 3 less than epsilon. And we add 3 to all the parts. Our goal, by the way, is to get this to be an x minus a. Sorry, that's our goal is to make it x minus 9. So I can say goal is x minus 9, and that gives us values we can use for our epsilon. So we have 3 minus epsilon is less than x, square root of x, which is less than 3 plus epsilon. So to get rid of the square root, we square all the parts. So we have 3 minus epsilon squared is less than x, less than 3 plus epsilon squared. And we need to have a 9 there, so we subtract the 9 from all the parts. So we have 3 minus epsilon squared is less than x minus 9, less than 3 plus epsilon squared minus 9. I forgot my minus 9 here, sorry. And this is, I mean, we're trying to pick our delta, and so the solution here is to pick the minimum of the two. It's very likely the minimum is going to be this 3 minus epsilon, assuming so epsilon is positive, so that should be what it is. But our delta would equal the minimum of these two things, which would be 3 minus epsilon squared minus 9, or 3 plus epsilon quantity squared minus 9. That's it. Okay, this is going to be a long lesson. Let's see what else we have here. Now we have the limit as x approaches -1 of x squared minus 2x plus 3. So again, we're going to go with let epsilon be greater than 0 and delta equals some blank. And given that it's a quadratic, we're probably going to have a minimum of two things again. Part of what we are dealing with, though, we have this x minus a, so it's the absolute value, so 0 is less than x minus -1, less than delta, so I'd say 0 is less than absolute value of x plus 1, less than delta. So we're going to get to a point that we'll be looking at x plus 1, and then, I mean, we're going to look at our f of x minus L and see how we can get these two to relate. Now, our absolute value of f of x minus L is less than epsilon, and that's going to be the absolute value of x squared minus 2x plus 3 minus 6, which is going to be the absolute value of x squared minus 2x minus 3, which is the absolute value of x minus 3 times absolute value of x plus 1. Hey, x plus 1, that looks familiar, doesn't it? Okay. So we're going to use this relationship here that we know this absolute value of x plus 1 is less than delta. And again, we do this approach a little differently now because we have to deal with the quadratic. So if I have this absolute value of x plus 1 is less than delta, that means negative delta is less than x plus 1, less than delta. And the goal is to make this look like the other one, the x minus 3. So if I were to subtract 4 from all the parts, I have negative delta minus 4 is less than x minus 4, less than delta minus 4. And like I did earlier, remember how I were to lower the lower limit? For this one, I want to increase the upper limit. So I'm going to make that into and I have a reason behind this, because if I factor out the negative on the lower limit, that's delta plus 4. I want to make it a delta plus 4 up on top, and I can do that. I can make the upper limit even further up, or the upper bound. So make that a delta plus 4. And now we're at the case that we have, that should be an x minus 3. Which was our goal, by the way. Okay, so we have the absolute value of x minus 3 is less than delta plus 4. So we choose delta equals to 1, which makes us the absolute value of x minus 3 is less than 5. So like we saw in the previous problem, it's going to go up to the top now. Delta will be the minimum of 1 and epsilon over 5. This 5 under the epsilon is the same 5 down here. That's where it comes from. So now we build it out. So we consider the absolute value of f of x minus L is the absolute value of x squared minus 2x plus 3 minus 6, which is the absolute value of x squared minus 2x minus 3 That's all part of the scratch work. Which becomes the absolute value of x plus 1 times absolute value of x minus 3. Well, the x plus 1 we found from above to be epsilon over 5, or from below. And we'll go with the one above. And then our x minus 3 is the 5, so we get our epsilon. Therefore, the limit as x approaches -1 of x squared minus 2x plus 3 equals 6. And that's it. Wasn't that fun? Okay, moving on. Another video to watch, and I have another try it. And let's do this last one here. Limit as x approaches 1 of x squared equals 1. So it says let epsilon be greater than 0. Choose delta to be the minimum of 1 and epsilon over 3. So they already started that out for us. Since absolute value of x minus 1 is less than 1, we conclude the following. Adding 2 to both ends, we get 1 is less than x plus 1 less than 3. So hence the absolute value of x plus 1 is less than 3. And they want us to complete the proof. It'd be helpful if it's all on the same page, but okay. We have, so we go with our absolute value of f of x minus L is the absolute value of x squared minus 1, which is the absolute value of x plus 1 times x minus 1. So the x plus 1 we said was the minimum. We can say is it, well, sorry, x minus 1, that's our delta, is going to be the epsilon over 3. So here's our epsilon over 3. The x plus 1, we saw earlier, it was 3, and I'm going to do this inequality. So all that's less than 3 times epsilon over 3. So we're left with epsilon. Therefore, the limit as x approaches, is that 1? Yeah, it was 1. Of x squared equals 1. That's it. For this last one, if we look at, again, our 3x plus 4 minus the 10, that's our f of x minus L, less than epsilon, we have the absolute value of 3x minus 6 is less than epsilon. So 3 times the absolute value of x minus 2 is less than epsilon. Absolute value of x minus 2 is less than epsilon over 3. So if they're telling us that epsilon is equal to 0.5, so what I want to point out is 0.5 over 3 would be something like 1/6. So that would work. Okay. Well, I know this is a confusing lesson, and there's another part to it I want to get to, but hopefully this gets you some of where you need to go for doing the assignments. Okay, bye.